make sure it's charging. One more minute. Okay. Can you hear me in the back? So there may be a problem with the battery that it gets depleted. If you stop hearing me, could you shout, please? If you stop hearing me and you see me, still speak. So.
Is there trouble with the mic?
No, I think it's just that they're sort of not really, they look like they're uncharged. Like
Yeah,
this.
I mean,
I know.
When after Juan spoke, while Hong was speaking, one of them was charging up.
Okay, so hopefully one of them.
Had.
Okay, let's. All right, great. So today, the goal is to finally get to the second part of my lectures, meaning the geometric engineering part. But before that, I'll have to explain to you what the Postnikov 2 group is. So that'll take up some time at the beginning. And then once we close that chapter off, you can ask me questions about all these higher form symmetries, higher group symmetries, and then we pass to, geometric constructions of such things. Okay, so we're discussing higher form symmetries. And we said, well, we have the standard zero form symmetry that can be non-abelian, but then we have these GP, so P bigger than 0. These are abelian groups. And if I have a quantum field theory, I can have several of these. And so if I, for example, have G0 and G1, the question is, does the 0 form and 1 form always form just a product? So they act on operators completely independently, which is maybe something you would expect, because these guys act naturally on point-like operators, and these act on lines. So what a 2 group is, so this is just of higher form symmetries, a higher group or a 2 group is when G0 and G1 do not form a direct product. And the first example we looked at was, so the first type was these split 2 groups. And here we have a 1 form symmetry. And on the 1 form symmetry, you have a finite group G0 acting. And that sort of says, well, indeed, there's some non-trivial interaction between these two things. And that was sort of the hallmark of this, was that delta B, or dB if you want, is non-zero, and it's given in terms of the background for a 0 form symmetry. And this was, these two are backgrounds for 1 form symmetry. Yeah, and the example I gave you was a spin for n pure gauge theory. Which has a 1 form symmetry, which is Z2 times Z2. And here I'm indicating an S and a C. One acts on the spinor Wilson line, the other on the co-spinor Wilson line as a Z2 times Z2. And the G0 exchanges these. So this is a zero-form symmetry that exchanges these two. It also exchanges the Wilson lines. And so this forms sort of one of these split two groups. If you write this out in terms of the backgrounds, then you get this sort of equation. Okay, so this is what we discussed last time. There's a sort of a non-split two group, and these go under the name of so-called Postnikov type. But are there any questions about these split two groups to start with? So it's a, well, okay. I was hoping not to use the word, but here it is. It's a categorified group. So it's sort of like when you have, here you have groups which are like the zero form and the one form, and each one is group-like. But there's some non-trivial structure, and it's actually happening on the level of the topological defect. And so in that sense, it's some kind of more categorical version of that. Any other questions? So there are also continuous, I should make this comment, there are continuous two groups, which I'm not discussing. And they are maybe familiar from supergravity theories when, say, a P-form symmetry field, the gauge transformations talk to some other higher form, some other form field. So say a P and a Q form have gauge transformations that are not independent from each other. So those are, of course, they also exist. I will focus on discrete sort of versions of two groups. Okay, so what is a Postnikov type 2 group? And here it's really instructive to look at an example before we go into the mathematics of it. Because the example will tell you immediately, it'll be completely transparent what's going on, and then we'll feed in the math subsequently. So the example is, again, one of these spin groups, but now we're in the spin 4n plus 2. And what's different about these is, well, their one-form symmetry is now Z4. And that's not the same, right? It's a different finite group from Z2 times Z2. And if I have a pure spin 4n plus 2 gauge theory, that's the one-form symmetry, and I essentially have Wilson lines that are in the spinor representation and in the vector representation. And if I take two spinor lines and I fuse them, I get a vector Wilson line. So what I want to do is, oh gosh, it's like all this water. So what I want to do is add to this theory now fundamental matter. So I can add to this theory, so I'm not looking at the pure theory, but now I'm adding spin 4n. And I can add fermions and the 2NF fermions in the fundamental. So let's write it like this. So fermions in the vector, I should say here vector, in the vector rep. That's right, thank you. So you're counting credit, so that's definitely credit. So fermions in the vector representation. So the spin 4n plus 2 as a vector rep, I just take 2NF, many of these, and I now ask what is the symmetry? So what would you normally have said, right? We said if we add to, say, an SUN theory, fundamental matter, then these topological operators that were measuring the one-form symmetry can now be sort of undone, right? These lines can end, and I can sort of strip off this topological defect, and that sort of breaks this one-form symmetry. So what would you say is the one-form symmetry of this theory when I add vector matter? I have spin 4n plus 2. It has the one-form symmetry, which is Z4. In the Z4, the one charge is the spinor line, right? And so if I add the vector matter, I screen, so I basically now I can end with V. So I can't end the WS, but I can end the WV, yes? So what is the group? Z2. So that's what we would have said 2 days ago, right? So we say this is now equivalent to basically the identity line. So essentially, so that we would have said naively adding V matter reduces the one-form symmetry to Z2. However, I didn't just add one copy of the vector. I added sort of 2NF. So I have, in addition to this one-form symmetry, now also a non-trivial flavor symmetry group that acts on this 2NF. And so now I need to actually revisit whether this is really all there's going on. And this is where the two groups come into this. All right. That's a different conversation. Okay, so however, this operator that I put there, this O, so if I have this Wilson line, the W Wilson line in the vector, there's an operator now which is in the vector web, but it's also, this is with respect to the gauge group, it's also in a 2NF of the flavor. There's an SU 2NF flavor group. So this is something we would call G0. Right? So it transforms in this representation. So in fact, when I'm really careful, I should also keep track of this charge. And so then it's actually useful to look at not only how these local operators transform under the gauge charges, but also under the flavor symmetries. And so in fact, it's nice to actually keep track of the flavor charge and so in this case, if you think of this now as sort of a flavor group, and then there's a center of this flavor group, this transforms as a non-trivial representation under the center of this flavor symmetry. So in fact, this operator O, V tensor 2NF, transforms as a -1 in the center of this flavor group. And I can sort of, if you want, you could sort of weakly gauge this flavor symmetry and then think of this as like a one-form symmetry of this flavor symmetry group, and then it actually is sort of charged, and it sort of screens that center symmetry. So in fact, what really is happening is this vector Wilson line, gauge Wilson line, really is screened, but actually there's a flavor Wilson line emitting here. So what really this motivates is we should consider sort of in addition, the flavor Wilson lines and gauge right? So we said one form symmetry is Wilson lines or line operators modulo screening by local operators. Now I'm also saying, well, we can take into account gauge and flavor Wilson lines. So we have W and W flavor. And these are now equivalent if there exists an operator, right? So here we have W tensor W flavor. In this way. So it's a slightly more refined equivalence relation. If we forget about the flavor part, this is just how we define the one-form symmetry. So in fact, the one-form symmetry sort of will be part of this. Whatever, this set of lines, if I take the set of all these gauge and flavor Wilson lines modulo this new relation, and call this group here E, then of course the Wilson lines will, if I just forget the flavor, they will be part of this. So in fact, I can embed into this the one-form symmetry group. But I can also project out and ask what is sort of this quotient. And this will now sit purely in the center of the flavor symmetry. So this will be part of the center of this SU2NF flavor. Right? This was part of the Z gauge. This is gauge, and this is flavor. All right, so here we have a one-form symmetry quantity. Here we have a zero-form symmetry. It's dependent on the zero-form symmetry. And there's a group. This will again be a finite group, which in fact may or may not be just the product of these two things. And if it isn't, then there's a chance that you actually have a non-trivial two-group symmetry. Okay, so is this equivalence relation sort of clear? I'm just basically coupling this whole thing to flavor backgrounds, and now looking at the equivalence relation that we looked at for the one-form symmetry, now keeping track of also these flavor charges. Any questions? Yep. So it's essentially for me keeping track whether this local operator that I use to sort of end the Wilson lines or put junctions in, whether they are charged under the flavor symmetry or not. Because in this case, in the spin 4n plus 2 case, with this additional vector matter, right, here we forgot about this. This was just the one-form symmetry, and we said, oh, it's just Z2. But once I keep track of it, it actually is charged under the center of the flavor symmetry. And so now the flavor Wilson lines are just saying, I couple it to a flavor symmetry background, and I keep track of that. If you want, just think of it as weakly gauge the flavor symmetry, and I just sort of Wilson lines again for this extended group. Okay, so we're getting this sort of embedding of this one-form symmetry into this group, and then we project out, and this will be something in the center. So here, let's call this here C. So mathematically, what you have is one of these exact sequences. So this means just that at each point, it's exact. It means that whatever comes into here needs to go into the kernel of this next map. So this is sort of exact in the sense that this is actually, there's a 1 here. This is an embedding, so this is injective. And this is, so projects, so this is a surjective. And now this is the kind of setup. So here we have, this was our Z2. And in fact, this operator was in the fundamental. So in fact, it actually transforms in a Z2 of also the flavor center. So there's a non-trivial Z2 in there, where it transforms as a -1. So now the question is, what is this group E here? Right? But in fact, we already know that this actually, there's this operator, O, that transforms both in the vector. Where did I write this down? Actually, it's here. It's in the vector of the gauge and in the fundamental 2NF of the flavor. So in fact, this group here, for this particular example, this actually is non-trivial. And this actually is precisely a Z4. So whenever this extension is non-trivial, then you have a chance that this theory has a two-group symmetry. And I'll define what it means in 1 second. So the first observation here is the following. If C is non-trivial, is not the trivial group, then in fact the flavor symmetry is sort of the simply connected version, 2NF, modulo C over C. Right? Because this is exactly saying, well, there's a center of this flavor symmetry, and in fact, we should be modding out by this here. And this is saying that flavor center symmetry is non-trivial from this projection. So in this case here, this is Z2. Right, so in our case, C is Z2. And if this sequence, if star does not split, so if in star E is equal to C times G1, then we don't have a two group. There's no two group. But if E is not C times G1, then there can be now a relation between these two groups. This is part of the zero form, this is part of the one form symmetry. So then there's potential, so there could be, so this is a necessary condition for the two group symmetry. Now I said the two group is like in the split case, two groups are given in terms of a non-closure of the background field for the one form symmetry. So what we'd like to actually understand is what does this imply in terms of the background fields? So when I have one of these exact sequences, these imply, so star implies if I'm looking at background fields, so I'm interested in, now I really have to talk about cochains, so these are not necessarily closed. So these are cochains. So there's, what I'm interested in is in our space-time, so M4, with these G1 coefficients, whether there's a B2, and that's completely independent from the background for the flavor symmetry. Now, if I have this exact sequence, I also get a sequence on these two chains. So there's a C2 with the coefficient groups given in terms of these groups. So C2 and 4, C and 2, 1. So what actually are all these things? So this here is basically some kind of, whenever C is non-trivial, in our case C is non-trivial, this actually is measuring a characteristic class of this flavor symmetry bundle. And this here would be the background for our one form symmetry group. And if this is sort of non-trivial, because the sequence doesn't split, and this is non-trivial, you'll get a non-trivial sort of element here that's actually not closed. So this C2 here is in fact sort of W2 in this case, which is the obstruction to lifting the SU2NF mod Z2 to the simply connected SU2NF. Right? When C is non-trivial, our flavor symmetry group is now not just SU2NF, but SU2NF mod Z2. And so there's an obstruction, and this is called a Stiefel-Whitney class for these bundles, these SU2 mod Z2 bundles, and that's actually non-trivial. That goes into the fact that C is non-trivial here. And so now actually the question is, how can we lift this here back? And this sort of sequence in these code chains implies also an exact sequence in cohomology. And so there's some math, which I'm happy to explain, but maybe Hello? Hello? Okay. Any more? There was one more question, yes? Yes, that's always true, yes.
So you can engineer situations where even when you put in this vector matter, you still don't actually see.
Yes, you will have to look at the partition function on a specific space-time to maybe turn on certain background fields, sure.
Mm-hmm.